Hello, today I want to share the review of latent space model for road networks to predict time-varying traffic. It is a topic very related to my own research, and the report will be presented in three parts. The first part is motivation. Here you can see the paper wants to solve the problem real-time traffic prediction from high-fidelity spatial-temporal traffic sensor data sets for intelligent transportation systems and sustainability. And the main challenge they want to fix is that how to exploit complex topological dependencies and high dynamism associated with changing road conditions holistically. And they also point out some limitations nowadays. The first is the models nowadays are only simply combine the local information of neighbors with temporal information, and the typical models are AIMA and SVR, and another models including Gaussian process and hidden Markov model is computationally expensive and always require repeated offline training, which made the application much more computationally expensive. Now let's see what this paper did for traffic prediction. The basic idea of this paper is based on the framework of matrix factorization. As you can see here is the basic framework. The G is the network snapshot, which each row corresponds to a row network vertex. And for example, from node vertex 1 to node vertex 2, there may be a segment, so there may be a record of this road, which means that from this node to this node, there's a road segment, and the traffic speed of this road segment is 28.6. This is the one element of this matrix, and that's what we call network snapshot. And through matrix factorization, the network snapshot can be decomposed into three factor matrices. And the paper noted this matrix as latent attribute matrix and attribute interaction matrix. As you can see, in latent attribute matrix, each row corresponds to the latent attribute of a node, and this row multiplied with this matrix and then multiplies with this current, we can derive the x1. That's what the matrix factorization did. Then, as you can see, there is something special in latent attribute matrix. At first, as you can see, this one, each row corresponds to a vertex in the road network, and the latent feature is spatially correlated in view of transportation. So the author applied graph Laplacian to add additional constraint to this problem to enhance the spatial correlation. And then we also consider that the traffic feature is temporally correlated, which means that the traffic state of current step is related to the traffic state of next time step. So the paper introduced a transition matrix to model this transition. Okay, from the introduction before, here we have a problem to optimize, in which the observation of the network snapshot, network topology, and temporal transition are considered in terms of loss function. And the problem mainly includes three kinds of parameters: the latent attribute matrix, the attribute interaction matrix, and temporal state transition matrix. These three kinds of parameters will be updated iteratively according to the paper. And more straightforward, to update each parameters, we're just focusing on the corresponding subproblem, because at this time another parameters will be fixed. The author solved the optimization mainly by introducing a auxiliary function and then do gradient descent through some mathematical maneuver. The update can be conducted in form of multiplication, which means that once you initialize the parameters as non-negative, the parameters will be kept in negative through the update procedure. The detail of update derivation is attached to the appendix of this PowerPoint, and I have not figured out entirely. Welcome the further discussion. Another highlight of this paper is introducing incremental learning to ease the computation in traffic prediction or missing value recovery problem. Specifically, when given a new snapshot, we want to update latent space from UT -1 to UT. At first, we will still predict the new graph snapshot with the old latent space in this formula. And then we check whether the error is too large to bear. We collect the element index if the error is larger than a set threshold. After this procedure, we obtain the new graph snapshot, a candidate set, and an old latent space matrix, and then we can do further incremental learning based on these three elements. On the stage of incremental update, we focus on the vertex in candidate set, and the optimization problem consists of two parts. The first part requires conservative, which indicates that the update should not be too far away from the last state, since the transformation of traffic state is limited temporary. The second part requires the collective, which asks for collective prediction. And the author also introduced a method of Lagrange multipliers to deal with this problem. And I also welcome the discussion of derivation of the solution of this. In addition, the authors points out that the update order does matters. And let's have an intuitive example here. Here is the matrix factorization proposed by the paper. When we are giving the observation between node 7 and node 6, we get this, and we get this traffic speed of this segment, and then we can update the row occurrence 7 in latent space matrix, while the row occurrence of the 6 vertex is fixed at this time. But however, when the observation from point 6 to point 2 is given, we can update the current or row 6 in latent space. At this time, the current row 6 will be different from the one used for updating current or row 7, and that will introduce some troubles for this problem. To avoid this problem, the authors will update the parameters according to the reverse of the partial order. It means that the vertex is updated only after its downstream nodes are all updated. So you can see when the downstream node is entirely updated, and finally we can update the feature of this vertex, and there is nothing contradiction here. After learning, we can come to the application for real-time forecasting, and it has two specific considerations. First, apply global learning to all the previously snapshot is computationally expensive, and sometimes more snapshots cannot always promise high prediction accuracy. So the author introduced a time window to do this to figure this problem. While in the time window, incremental update is performed and then predict the next step. And then comes to the end of the time window. Here, the global learning will be implemented with all snapshots at current time window. Now let's come to the empirical study of this paper. The dataset this paper used is a 2-month traffic sensor dataset which is collected from Los Angeles County highways and arterial streets. And there are 2 subgraphs of Los Angeles road network from HeuroMag dataset. The author divides this dataset into 2 parts. The small part includes 5,984 vertices, 12,538 edges, and 1,642 sensors, while the large dataset includes more vertices and edges and corresponding sensors. The paper conducted multiple tests to verify the model. The first test is the one-step ahead edge traffic prediction, and the models to analyze and compare includes the global learning model, which is proposed by this paper in this formula with this optimization problem, and the incremental learning also proposed by this paper, which has introduced before. And the comparison is the first comparison model is the LSM iron naive, which basically with this 3 procedure. First, the metric factorization is implemented to impute the traffic data and get the latent traffic feature, and then they try to solve this optimization problem to get the state transition metrics, and then they do the traffic prediction based on this formula. As you can see, the basic distinction between this model and this model is that they separate the temporal learning scheme from the original optimization problem, which means that some temporal interaction is essentially lost because these 2 parts are separated. And they also conduct the traditional traffic prediction method AIMA SVR, and for fear they also use the completion reading from this model to predict based on the complete dataset. And the conclusion of this test is that the LSM iron naive performs worse than the proposed model because it treats the latent metrics separately. And the SVR and AIMA perform worse due to the missing data. And although the missing data in 6 is completed, they also performs worse. And also we can see the SVR is more robust to AIMA giving missing data due to the ability to model nonlinearity. The second test is the multi-steps ahead edge traffic prediction, and the models to analyze and compare is the same as the text 1. And the major conclusion of this text is that the margin between proposed models and the baselines is narrower due to the inevitable error accumulation resulting from using predicted value for further prediction. And now let's come to the text 3, which is the missing value completion. Here, the proposed model is compared with the naive model and the nearest neighbor method, a traditional machine learning method. And so this text, the main conclusion, including the proposed the global learning model performs better than the incremental learning model by jointly inferring all the latent attributes. And a naive model and KNN have similar performance, which is inferior to the proposed model methods. And there, the last task is the real-time forecasting, which is based on 3 models. The first 2 are the proposed models, and the third is the naive models, which not update the latent space when given new available data. So this task, the major conclusion is that the incremental learning model is the most efficient because it only considers a small portion of network at a time. And there are another task which is not focused on the model ability, but the parameter sensitive analytics, which is to test the parameters of influence of this model. First, they test the effect of varying t. The t is the time horizon they consider for the optimization problem. And the conclusion is that at first the prediction performance will improve as they increase, but then become stable. And another parameter they want to analyze is the effect of varying span, which is the time gap between 2 snapshots. Because as you can see, the 2 snapshots can be updated at different time steps, and let's see how far these 2 time steps extrapolated will influence the model. And naturally, we can see that the prediction performance declines as span increases. And the last is the effect of varying k, which is the number of latent variables, and the lambda, which is the regularization parameters. And through the text, at first the prediction performance will improve as k increase. Then the influence becomes less significant, which means that the latent traffic state, the dimension of latent traffic state will be important to the prediction at first, but while the dimension become large to some extent, its function did not so exclusive. And another conclusion is that the global learning is more sensitive to the lambda than incremental learning. Okay, that's all the review today, and welcome for the discussion and any problem from you guys, and you can put your problems or opinions on the blog below. Thank you.